Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous lecture, we have started with the surface water and we have seen what is meant by surface water, and the water which is flowing on the surface of the earth is termed as surface water. And after that, we have seen different storage components. Once these storage components are satisfied, we will be getting the surface water. And we have already seen the abstraction, that is different losses which are taking place from the rainfall. Whenever there is a rainfall occurring, we are having infiltration, and also we need to satisfy different storage components. After that, whatever excess rainfall is coming, that is coming as the overland flow or surface runoff. So, we have seen different techniques to calculate the initial abstractions. In those abstraction techniques, we were discussing about the initial abstraction and also water loss due to infiltration. So, different abstraction calculation techniques we have seen, and remaining water is considered as the excess rainfall or direct runoff depth that will be contributing to the direct runoff or overland flow. So, in today's lecture, we will move on to overland flow. So, the flow of water over watershed varies in all the three dimensions. So, it is a three-dimensional phenomenon. In all the direction, the flow of water on the surface of the earth will be taking place. It begins when water becomes ponded on the surface at sufficient depth to overcome surface retention forces and then begins to flow. That is, whenever there is a storm or rainfall is occurring, we are having certain storages to be satisfied. Once these storages have been satisfied, the remaining water which is coming is termed as the excess rainfall. This excess rainfall will be initially ponded on the surface of the earth. Once it reaches certain depth, it will overcome the retention forces and it starts flowing on the surface of the earth. So, that is termed as the overland flow. Two basic flow types may be distinguished as, one is overland flow and the other one is the channel flow. Overland flow is the flow which is having a thin layer of water flowing over a wide surface. Once the depth is attained to certain level, excess rainfall depth is attained to certain depth, it will be overcoming the retention forces and it starts flowing on the surface of the earth. So, that is the overland flow, and once it has started as overland flow, it cannot flow as overland flow or sheet flow for long time. As the area increases, what will happen? It will be separated into small channels. So, then the channel flow starts. Both this overland flow, that is the sheet flow, and also the channel flow are considered as the surface flow. And the channel flow has a much narrower stream with water flowing in a confined path. Overland flow, it is spreading over the entire area, and after that it will be concentrated into small channels. On a natural watershed, overland flow is the first mechanism of surface flow. That is, initially different storage components will be satisfied. After that, water will start accumulating on the surface, certain depth it will be attaining, then the first flow process which is starting on the surface of the earth is the overland flow. And the importance of this is that it exists only for a short distance. It cannot go beyond a certain distance. After that, what will happen? Non-uniformities in the watershed surface separates the flow into different channels. It will not be a plain surface. The land surface will be having so many undulations and non-uniformities. It will be leading the overland flow to separate it into small channel flows. Gradually, the outflows from these small channels combine to produce recognizable larger channel, and it flows to form runoff at the watershed outlet. Initially water depth, and then it will be flowing as overland flow, and overland flow again due to the non-uniformities separates into small channels, and it will form recognizable channels, and these channels will be contributing water at the outlet of the watershed. That is our runoff. Now, surface water flow is governed by continuity principle and also momentum principle. Here also we will be making use of our fundamental principle, that is the continuity and momentum principles. So, overland flow is a thin sheet flow which occurs at the upper end of slopes before the flow concentrates into recognizable channels. So, now consider a flow down a uniform plane on which rainfall intensity is high and the infiltration rate is small f. So, we are going to find out the expression for quantifying the overland flow. So, for that what we are considering? We are considering an inclined plane on which we are getting the rainfall which is having an intensity I and also infiltration small f. So, these are the two inputs, rainfall intensity I and infiltration rate small f. Now, sufficient time has passed since rainfall began and the flow is considered to be steady. So, here we are going to derive the expression for overland flow considering the flow to be steady, and the expressions will be derived based on the fundamental principles of continuity and momentum equations. Now, what we are going to do? We are going to consider a plane which is having a length L0. So, we can see the schematized representation of the plane. It is having a length capital L0, and the x direction is considered as along the plane and y direction is perpendicular to the plane. So, you should keep in your mind that x is not horizontal, x direction is considered along the plane and y is perpendicular to the plane. We are considering a length of plane as capital L0 and width in the other direction is considered as unity. That is, the plane is an inclined plane. So, it is making an angle of theta with the horizontal, and based on that we will be having a slope that is given by tan theta. So, slope is given by tan theta because the inclination of the plane is theta with the horizontal. Now, what we are going to do for the analysis point of view, we need to consider a control volume that is represented by means of this dotted line. This is our control volume, and the rainfall is occurring within the control volume which is having an intensity of I, and from this infiltration rate is represented by small f is taking place. And whenever a rainfall is occurring, water is getting infiltrated into the ground, and after that once the initial storages have been satisfied, we will be getting a ponded depth of water on the surface of the ground. That is, the excess rainfall will be causing the ponding depth, and once it is free from the retention forces, it starts flowing as a thin sheet flow. That is our overland flow which is having a depth of small y. That y is measured perpendicular to the plane along the y direction, and the velocity is along the direction of x, that is represented by v. So, the depth y is measured perpendicular to the bed and velocity is measured parallel to the bed. This is the same representation which I have shown in the previous slide, and Now we need to write the continuity equation. When we are going to write the continuity equation, we will be making use of Reynolds transport theorem, which is given by this equation. This is very much familiar to you. We have been using it continuously for different processes, and in this case we are considering steady state of flow. So, when steady state is considered, with respect to time there will not be any variation. So, you look at the RTT, we are having two terms, one is on the left hand side dB by dt of the system, and on the right hand side the first term is also d by dt of across the control volume beta rho dV. So, both are unsteady terms. So, for steady constant density flow, the equation takes the form across the control surface beta rho V dot dA equal to 0. So, beta rho V dot dA, what is beta? Beta is the intensive property. That intensive property is calculated based on the extensive property. In this case, this is the flow of water, and while considering the extensive property and intensive property, this is mass conservation principle. So, the extensive property capital B is the mass of the fluid, and corresponding intensive property is dB by dm, that is equal to 1. And here we are considering constant density flow. So, density can be taken out of the integral sign. So, the equation takes the form surface integral of V dot dA is equal to 0. RTT has taken this simple form. What does it represent? It is representing the net outflux equal to 0. That means inflow is equal to outflow. Now, before further proceeding, we need to see the cross section of the control volume. So, the control volume is having a unit width and intensity of rainfall I entering into the control volume. F is the infiltration taking place from the ground surface, and because of the sheet flow is having a depth. The depth of sheet flow is represented by Y, marked like this. Now we can write the inflow and outflow. Inflow to the control volume from rainfall, that is main inflow is from rainfall, and outflows are due to infiltration and also overland flow. So, we can write expressions corresponding to inflow and outflow separately. So, inflow to the control volume can be written as I L naught cos theta. This is discharge per unit width, because we are considering the other dimension as unity. In the similar way, we can write the outflow due to infiltration, that will be F L naught cos theta. L naught is inclined at an angle of theta. So, the component of that along the horizontal will be L naught cos theta. So, that is why L naught cos theta multiplied by 1 into per unit width we are considering. That is why it is F L naught cos theta and I L naught cos theta. Now, when we talk about the overland flow, discharge per unit width is given by V multiplied by Y. So, overland flow can be written as V multiplied by Y. Now, we have written expressions corresponding to inflow and outflows. We can substitute in our Reynolds transport theorem. Inflow is I L naught cos theta, outflow together, infiltration and overland flow together, we are considering F L naught cos theta plus V y. So, in this case inflow is equal to outflow, because we are considering the steady state condition. So, continuity equation is written as I L naught cos theta minus F L naught cos theta plus V y is equal to 0. And what we are going to quantify? We are going to quantify the overland flow. We need to quantify the overland flow. So, that quantities corresponding to overland flow will be kept on the left hand side, other terms will be taken to the right hand side. So, we can write V y is equal to I minus F L naught cos theta. So, V y is representing the overland flow, discharge per unit width. So, how do we represent that? We will be representing discharge per unit width as Q naught. Q naught is equal to I minus F L naught cos theta. Discharge Q naught we have obtained, and on the right hand side we are having I minus F L naught cos theta. So, for solving this we need to have one more equation that will come from our momentum equation. So, momentum equation when we derive, we are going to take some concepts from fluid mechanics. That is, from the concepts of fluid mechanics we can write, for a fully developed laminar flow taking place over an inclined plane, the velocity can be written as V is equal to rho g sin theta divided by mu multiplied by y square divided by 3. So, this equation is coming from fluid mechanics. You might have already studied in the course of fluid mechanics in the case of fully developed flow occurring over a fully developed laminar flow occurring over an inclined plane. So, for that flow the velocity is given by this expression. We are not going to derive that particular equation, we are directly taking it from fluid mechanics. So, here also in our case we are considering a flow, laminar flow over an inclined plane. So, in this equation mu by rho can be substituted as nu. Nu is nothing but the kinematic viscosity, and the expression for velocity takes the form g sin theta y square divided by 3 nu, where g is the acceleration due to gravity and nu is the kinematic viscosity of the fluid. And one more term is there related to sin theta. In the case of small angles, from calculus we know that sin theta equal to tan theta equal to theta. So, here for sin theta we can substitute as the slope. So, the expression takes the form, for uniform laminar flow on an inclined plane, the average velocity V is given by V is equal to g s naught y square divided by 3 nu, where s naught is sin theta. This assumption is applicable to very small angles only. So, for sin theta we have substituted as the slope of the plane, and the average velocity is given by g s naught y square divided by 3 nu. So, this expression can be used for finding out the velocity of overland flow. Now, what we are going to do, we are going to combine the continuity equation and also momentum equation. For uniform flow we know S naught equal to SF, that is the bed slope is equal to friction slope. That can be written as HF divided by L. HF is the head loss as the flow takes place from one location to another which is having a length of L. HF divided by L will be giving us the slope or the friction slope, HF divided by L. So, from that we can write HF is equal to L S naught. L multiplied by S naught will be giving you the head loss taking place during the travel of a distance of L. V is the expression for V we have already written, g S naught y square by 3 nu, and what we are going to do, for S naught we will substitute 3 nu V divided by g y square in this equation. So, HF can be written as 3 nu VL divided by g y square. This equation can be again modified as 3 nu VL by g y square multiplied by 8V divided by 8V. We need to rewrite this equation in some other form. That is why we are going to multiply and divide this particular expression on the right hand side by 8V. So, it will take the form HF is equal to 24 nu divided by Vy L by 4y V square by 2G. Why we are writing this? We know already from Darcy-Weisbach equation, flow resistance HF is given by FL V square divided by 4R 2G. You compare these two equations, you can see that both these equations are of the same form. Here you can see V square by 2G is there on both the equation. In the first equation we are having L by 4y. Instead of that, in Darcy-Weisbach equation we are having L by 4R, and R is nothing but R is equal to Y hydraulic radius. So, by comparing this equation and the Darcy-Weisbach equation, we can conclude that R is the hydraulic radius, that is depth of overland flow can be considered as the hydraulic radius R. Both are same. and F can be written as, friction factor F can be written as, we are having F and 24 nu by Vy. While comparing these two equations, we can understand that both can be equated. So, F is equal to 24 nu by Vy. That is what we have obtained over here. That can be written as 24 nu by Vr. Friction factor F is given by 24 nu divided by Vr. But we know in the case of a pipe flow, R is equal to D by 4. Hydraulic radius R can be written as diameter divided by 4. This is coming from the expression hydraulic radius equal to A by P, area divided by wetted perimeter, and from that we can understand that R can be written as diameter divided by 4. So, D is the equivalent pipe diameter, and here we are substituting for R as D by 4, it will be taking the 4 96 nu by Vd. Friction factor F is equal to 96 nu by Vd. Now you look at the equation, it is very much familiar to you. Keep aside 96 nu by Vd. What is Vd by nu? Vd by nu is nothing but our Reynolds number. So this equation can be modified as, friction can be rewritten as 96 divided by Re. Re is nothing but the Reynolds number given by Vd divided by nu. For laminar flow, Reynolds number should be less than 2000. So, we have considered initially when we were discussing, we have considered the flow to be laminar, and HF is given by, that is taken from the previous slide, FLV square by 4R 2G from Darcy-Weisbach equation, and for uniform flow Q naught is equal to Vy. Q naught is equal to discharge per unit width is given by V multiplied by Y. That is our expression for overland flow. So, now what we are going to do, V is equal to Q divided by Y. We know HF by L is equal to FV square by 8GY, and from this we can write HF by L is nothing but our bed slope or friction slope. For uniform flow both are equal. S naught is given by FV square divided by 8GY. V square is given by 8GY S naught divided by F. So, here we are having V and also here we are having V. So, what we will do, we will substitute V is equal to V square is equal to 8GY by S naught. In this equation we will substitute this. So, let us see how it will be coming. That is Q by Y whole square, V square is equal to 8GY S naught divided by F. So, we can modify this equation, Q square divided by Y square is equal to 8GY S naught by F, and Y cube will be taking the form FQ square divided by 8G S naught, which will give us the value corresponding to the depth of overland flow Y is equal to Fq square divided by 8G S naught all to the power of 1 by 3. So, this is the equation corresponding to the depth of overland flow. How did we get that? We have combined the continuity equation and momentum equation, and while using the momentum equation, we have made use of the principle from fluid mechanics regarding the velocity of a fully developed laminar flow over an inclined plane. Friction laws, we have compared the head laws from that equation and also from Darcy-Weisbach equation, certain adjustments with the terms we have done, and finally we got the depth of overland flow given by this equation, Y is equal to Fq square divided by 8G S naught all to the power of 1 by 3. And this Y specifies the depth of laminar sheet flow. This is the depth of laminar sheet flow because our assumption initially is flow is a fully developed laminar flow. Now, if what will happen, the flow becomes turbulent case. If flow is turbulent, we cannot make use of that formula. Friction factor becomes independent of the Reynolds number. Turbulent flow, Reynolds number is not coming into picture. It is independent of Reynolds number and dependent only on the roughness of the surface. Roughness of the plane surface it will be dependent on. So, we can make use of Manning's equation in that case to describe the flow, that is given by Q is equal to 1 by N AR raised to 2 by 3 S naught to the power of half. So, if the flow is turbulent, we will not be making use of the previous expression for depth of flow. We will be making use of the Manning's equation and we will find out the depth of flow by making use of iterative techniques. And here in this case, hydraulic radius r can be taken as depth of flow, Q naught is Vy and V is given by 1 by n r raised to 2 by 3 s naught to the power of half, and for uniform flow V can be written as 1 by n y to the power of 2 by 3 s naught to the power of half. So, V is again written as Q naught by y equal to 1 by n y to the power of 2 by 3 s naught to the power of half, which gives y is equal to nq divided by s naught to the power of half all to the power of 3 by 5. By comparing this equation for turbulent flow and also for laminar flow, you can make it in a general form that I am not doing over here. That is, if the flow is turbulent, that you can understand by computing the Reynolds number. If it is greater than 2000, you can make use of this formula to get the depth of overland flow y. If the Reynolds number is less than 2000, it represents the laminar flow. So, in that case, the expression which is derived based on the fully developed laminar flow, we can make use for finding out the depth of overland flow. So, that much about overland flow. Now, let us move on to channel flow. Consider a channel length LC, L subscript C, it is representing the channel length that is fed by the overland flow. That is, initially itself we have understood that when an overland flow is formed, it will not be continuing for long distance. After certain time, it will be separating it into small channels and finally concentrating into a well defined channel. So, here what we are assuming, there is an overland flow that is contributing flow to the channel which is formed. So, that channel is having a length of LC. So, here we are having the overland flow and within that overland flow we have considered unit width only. So, the flow is entering into a channel. Overland flow has a discharge Q naught per unit width that is discharging into a channel which is having a length given by LC. This is the schematic representation of our channel flow. And the channel is having a slope. Based on the slope, flow is taking place. And the total discharge from the channel is represented by Q. Q is given by Q naught multiplied by LC. So, here we have considered the width as unity. In the similar way, entire sheet flow is coming to the channel. That is why for getting the total discharge coming to the channel, we need to multiply discharge per unit width by the length of the channel. Here the total width of the sheet flow is the length of the channel. That is why capital Q is Q naught LC. So, that is the outflow from the channel. That Q is given by the channel flow. To find the depth and velocity at various points along the channel, an iterative solution of Manning's equation can be used. So, here we are having a discharge Q from the channel and we are assuming that it is a uniform flow. That Q, how it is produced? It has come from the sheet flow. So, entire sheet flow is contributed to the channel and we are considering the value capital Q as small q multiplied by the width of the sheet flow, that is nothing but the length of the channel. So, that Q can be assumed as uniform flow and by making use of the iterative techniques you can find out the solution to get the depth of channel flow. So, that iterative technique I am not explaining over here, so that you can refer into any of the textbooks. Now, coming to the travel time. How much is the time taken by the flow to travel from one point to another, or when the flow will be reaching at the outlet point? That is our next aim. So, travel time of flow from one point on the watershed to another can be calculated from the flow distance and velocity. That we all know, if we know the distance travelled and the velocity which we have calculated from the previous expressions, in the case of overland flow and also in the case of channel, we can calculate the travel time. How much time the flow will be taking to travel from one point to the outlet of the watershed. So, distance between 2 points on a stream be L, and we are having the velocity along the path connecting them as VL. So, we can calculate the travel time T as dl by dt. dl by dt is equal to VL. VL we have computed and we know the length. So, then we can get dt as dl by VL. So, dt is the time taken for travelling a distance of dl with a velocity of VL. So, t can be obtained by integrating it from 0 to t for travelling a distance of 0 to L. So, this can be written as t is equal to integral 0 to L dl by VL. So, we can get the travel time the flow has taken from one point to another. If we know the distance and we know the corresponding velocity, we can calculate the travel time, where L is the distance along the path. And if the velocity we are assuming constant at Vi, that is we are considering different increment. At the ith increment we are considering Vi as the constant velocity. In the similar way, in all increments we are considering constant velocity, calculating the time for each segment, and finally total time is calculated by summing up all the times for each increment. So, that way we can get the total time taken by the flow to travel from a particular point to the outlet of the catchment. Now, because of the travel time to the watershed outlet, only part of the watershed may be contributing to surface water flow at any time once the precipitation begins. You can imagine we are getting a precipitation over the watershed. Entire catchment won't be contributing flow at the outlet point initially. Extreme point will be contributing flow at the outlet point after taking some more time. More time is required for the flow to travel from the extreme point to reach the outlet point. So, initially certain part of the catchment will be contributing flow towards the outlet point. We can have the schematic representation of that. Let this be a watershed and we are having the stream networks, and the outlet of the watershed is represented by B, and the extreme point is represented by capital A marked by this red dot. Growth of the contributing area takes place as time increases. Initially, entire watershed won't be contributing water at the outlet point. The growth of the area takes place as time increases. So, initially at time t1, this much area will be contributing water to the outlet point. Only this much area will be contributing. And as time is increasing from T1 to T2, more area will be contributing water at the outlet point, which is marked by the area contributing to the outlet. Area contributing flow to the outlet point is marked by green dotted lines, and it takes more time than that of T2 for water to reach from this point to last point, outlet point B, that is the remotest point to the outlet point B. So, the time at which all the watershed begins to contribute is termed as the time of concentration Tc. This time of concentration Tc is very important whenever we are talking about the flow taking place at the outlet of the watershed. So, this is the time of concentration is the time of flow from the farthest point on the watershed to the outlet. Which is the remotest point in the watershed, that point will be contributing flow at the outlet of the watershed by taking a time of concentration. Now, we need to understand certain concepts related to stream networks. So, the quantitative study of stream network was originated by Horton in the year of 1945. It is based on Horton's theory, and we need to understand the terminologies used by Horton, that is Horton stream ordering system. So, this is very important as far as watershed hydrology is concerned. So, Horton stream ordering system includes the smallest recognizable channel is designated as order 1. So, in a watershed there will be so many channels present. smallest recognizable channel. That is, once the overland flow separates into channel flow, small channels will be produced. Later on, as time elapses, recognizable big channels will be produced. So, the smallest recognizable channels are designated as order 1, and these channels normally flow during wet weather only. Flow will be present in these channels only during the monsoon season. And when two channels of order 1 joins, a channel of order 2 results. If two channels of order 1 joins together, we will get a channel of the order 2. That is, in general, if you are telling two channels of order I join, a channel of order I plus 1 results. That is, when two channels are having order 1 channel meeting another order 1 channel meeting together to form a channel which is having a stream order of 2. If we are generalizing, two channels having order I join together, then we will be getting a channel which is having a stream order I plus 1. A channel of lower order joins a channel of higher order, the channel downstream will be having an order of higher order. Out of the two orders, highest order will be given to the channel which is formed out of these two. The order of the drainage basin is designated as the order of the stream draining at its outlet. Finally, these small recognizable channels will be meeting together to form a big channel, and the order of the catchment or watershed is given as the order of the channel which is meeting at the outlet point of the watershed. So, this can be more understood by means of a figure. Let this be a stream network in a watershed, and in this we are going to do the stream ordering. So, two streams which are having order. So, these are the two channels which are having order 1, those two meeting together to form a channel of order 2. Then we are having another stream which is meeting this stream which is having order 2. The order of this stream is 1, and these two streams are joining together. We are getting a new stream number, that is nothing but order 2. And we can continue like this. These two streams having order 1 will be joining to form a stream having order 2. And now we are having, in the similar way, there also order 1 channels join to form the channel to have stream order 2. Here also in the similar way it is formed, and now two channels which are having order 2 joining together to form a channel having a stream order 3. In the similar way, here also we will get a channel of order 3. Now these two channels will be joining to form a channel which is having an order 4. Now two channels are joining which is having order 4 and the other one is having 1. The channel which is meeting at the outlet will be having order 4. So, stream order of this watershed is 4. This way we need to order the streams. So, manually doing this will be difficult, but this can be easily done in any of the GIS softwares. So, the order of this drainage basin is 4. That I think it is very clear with the help of this figure. Now, we need to understand the characteristics of stream networks. So, first one is the drainage density. Drainage density is nothing but the ratio of the total length of all stream channels of the catchment to the catchment area. So, it indicates the drainage efficiency of the catchment. If higher the drainage density, runoff will be faster. If we are having a watershed which is having higher drainage density, the runoff will be reaching at the outlet in a faster rate. Drainage density is represented by DD. It is given by an expression LS divided by A. It is the ratio of the total length of the streams to the catchment area. LS is the total length of all the streams and A is the catchment area in kilometer square. Next one is the stream density. It is defined as the number of streams ns of a given order per kilometer square computed by dividing the total number of streams of the same order of the catchment with catchment area A. It is the number of streams divided by the area of the catchment. So, stream density is given by ns by A. Ns is the total number of streams of given order and A is the area of the watershed. So, here I am winding up this lecture and the references related to this topic are given over here. Thank you.